Hello everybody, my name is Barsha and we will today talk about maybe the most important thing in CUDA programming, and that's it. That's the how to turn kernels into threads. What is the kernel? Kernel is actually the function which is executed on GPU, and how to recognize a kernel inside the CUDA program that we write. It has identifier global old or device that we already mentioned in some short videos in front of its name. So there is first specifier, global or device, and then it comes names of the function. So kernel is actually the function which is executed on GPU. First thing we do is actually to define kernel or kernel function, and then later in main program we calling that kernel function or kernel or whatever. But then when we call it, we usually use this, let's say, brackets in form of a bigger or lesser than, and inside we put some dimensions. Usually here we write number of threads in block, and here we write number of blocks in grid, but we will discuss more about that later. And this part is actually calling kernel function in main program. So you have main program, and we call in main program, which is going, let's say, execution is going on a host, and then we jump into some kernel function, which is recognizable and defined by global, and also usual thing which comes up is this, let's say, crazy brackets where we put here some numbers, and as it says here, these identifier or specifier, or actually it is called execution configuration. So we put here execution configuration, and that shows us the way and number of these copies of this function, which is named the name of kernel. We specify here number of copies and how they are distributed through the dimensions, and we make here, actually, when we derive here number of copies of this program, which will be turned, and these copies of this program will be turned into, let's say, threads, and wait for execution with some schedule. So this here, which is shown here, is called execution configuration or kernel launch configuration. It shows us actually how, as I said, how we execute these functions or copy of the functions, and how many copies of this function we have. So, and this one is called execution configuration or kernel launch configuration. Combination of numbers given inside of it. So this combination of numbers with some rule how we create number of this number, how we create these numbers of copies that we create out of this kernel. There's some rules, yes, and then for this example we put here basic simple numbers, straight numbers. So total number of threads will be 256 times 1. So 256 threads in one block. If there is a 2, then it will be 2 times 256, and that will be number of threads which will be formed, or number of copies of this function which will be created in the process. But we will talk about this later a little bit. Let's stick with the what's going on here. Combination of numbers given inside of it means here represents total number of threads. So according to some rules, we create number of threads or copies, as you can see here, out of this function or kernel function which will be executed. So inside of it represents total number of threads. So we have total number of threads, total number of copies of kernel function with indexes assigned to them. So to mutually make a difference between these threads or copies of this kernel function, we assign uh, to every thread we assign some index to it, so we can recognize and make differentiation between these threads. So every one of them actually executing same function, but they are, let's say, on a, they are not mutually, let's say, connected. Those are executions, or should not be mutually dependent. So every copy doing for itself, and when it finishes, so there's some flags pulled out to, let's say, uh, to say I'm done, I'm done, I'm done, I'm done, I'm done. So total number of copies, as we can see, of kernel function, which is here we make multiple copies of these kernel functions which execute on some different or specific data, and every of these threads have some index which is assigned to them, as we can see here, but we will discuss more of that later. Total number of copies of kernel function with indexes assigned to them. Okay, in these examples, if here this is dimension of the block, and it's obvious it's one dimensional. So we have 256 threads in one block, and here is number of the blocks. We have one block, so everything is clear here. The 256 times 1 is actually 256. In this case, number of threads, and so we will have thread indexes 256, which corresponds to number of threads. So every thread have its own indexes. So program can manipulate and make differentiation between threads, and have let's say some reference to access to a specific thread through that index if there is a need for it. So inside of every of that threadIdx actually have some specific value. So inside the body value for this thread 0, threadIdx.x have this value. For thread number 1, threadIdx have these numbers. So every thread have different value of these built-in variable inside of itself. So we will see that in examples, but this is reference to inside when we call this built-in variable inside the body of a kernel or thread. It have its own value, so not to mix with our. The name is same, but every function, the domain value of that variable is inside of that, let's say, name of kernel name, or inside that function, but it assigned locally and in parallel to all of these let's say copies of the thread. So every copy of this function have its own value of that built-in variable, which have range inside of the body of that function or kernel. So we have 256 threads and 256 indexes according to this calculation here. And indexes of threads in this case are given in threadIdx.x built-in variable for specific thread, and takes values from 0 to 255. 55th, funny. From 0 to 255, and so these built-in variables have range, as I said, inside of the thread, and for specific thread that values have fixed value, and every thread have let's say dedicated or assigned value of this built-in variable for itself. So actually there is a 256 values of this built-in variable for every specific thread. We will see later in examples, but there is also some examples that we showed, but I think it's on Serbian. But anyway, we will do the program and check how it's going in real, let's say, program, what is going on, and to see the confirmation of what I said in this, let's say, theoretical explanation. What can we say else about this? So yeah, every thread is actually a copy of this function, and it's scheduled to be executed according to some rules. These are formed to be executed in parallel because it's mutually, these threads are mutually independent, let's say, execution or functions which are waiting scheduled to be executed, with only difference probably in this case is they are, let's say, executing on parallel, executing parallel on a different course. That's what we assume, and every one of them, if you want to use this built-in variable, using actually specific built-in variable which is assigned to itself. So there is a 256 copies or threads of this function, which is using probably in body this built-in variable. And that's how we actually parallel executing these, let's say, functions or programs, or using parallel execution if some things are not, let's say, mutually dependent, to parallel and independent execute these copies of this program with different values of these built-in variables. So I hope this was not too much confusing. I tried to explain. So there's kernel definition, there's calling a function, and then when we call the function according to this value, we creating the threads with different indexes assigned to them. So that's the full story, and there is a different ways to manage number of threads, number of blocks in grid inside of it, and we will go through that process in further videos more deeply, and see how to optimize our, let's say, multiple copies with different indexes to be executed in parallel, and speed in time. So also important thing to say is that this is used, or we pick up functions which can easily be done in this process in CUDA programming, or in CUDA cores, or in tensor cores. So there is no things that are executed here in this way actually are more simple. The body of this kernel is more simple in sense of it's more oriented to easy algebra calculations than some complex instructions that needs to be done in sense of calculation, but in sense of leading the process. That for that purpose we have CPU, but things are easily manageable on GPUs, and these are like, let's say, adding the arrays, matrix multiplication, and so on. So I think this is enough for this intro, and we will see in details how to optimize this interior here for more parallelism achieving in this process, and also which that also implies more speed in execution of the program. Let's say in general when we looking for. This also contributes to thing that we avoid also for loop because we are making multiple copies. So we don't have to go through the iterations because we have multiple copies of these programs which we execute in parallel. So we are avoiding these, let's say, for loop iterations, which we know from the standard way of programming. So not to complicate too much, I think this is enough for this first time, and we will go in details later.